Yes, can anybody hear me? Good morning, everyone. So I'll be talking mostly about earthquakes around plates because this is something we understand much better than earthquake inside plates. A few preliminary remarks before I go into the hard science. There's often a misconception in the public about large earthquake, and I'll be talking about large earthquakes. In the public, large earthquakes are those who kill people. And for us scientists, a large earthquake is an earthquake that releases a lot of energy. And you can see from this slide, there are about 20 to 30 so-called very large earthquakes, the earthquake that killed more than 10,000 people in the past, over the last century. And many of them aren't so large, including the biggest or the one that killed the most people in 2010 in Haiti, which was actually a relatively small magnitude compared to the Japanese one, the one which was on my first picture, who killed, in quotes, only 20,000 people, which was a very, very large magnitude, one of the biggest earthquakes that was ever measured. Second thing, the impact of earthquake is, contrary to what most people think, growing. You should think that elaborated societies with more technology have more capacity to be resilient to earthquake, and it is the other way around. That's an image taken in 1960 after the largest earthquake ever, the Valdivia earthquake of 1960. And this is one taken after the Japanese earthquake of 2011, and it's easy to understand what's going on. The level of damage is related to the magnitude of the earthquake, but only slightly. It is mostly related to how many buildings you have where the earthquake happened. And our societies are building more and more and more and more, and sometimes not so robust infrastructures, which means that when we have an earthquake now, the number of people who die may change by a lot, but the damage in billions of US dollars is steadily increasing towards extraordinary amounts. So that's the impact of earthquakes on our modern society. Now, if we go back to large earthquakes, the first question people ask is how many we have. And they think we have few of them. The one they may hear about on TV. And of course, it's really not the case. On this map plot here, you have more than 100 of earthquakes, all of them of magnitude larger than 7.5, which occurred over the last century. And the first striking feature about this plot is that the extremely large earthquake, the one we call the giant earthquake, they are rare, or they were thought to be rare because of a long period of 40 years, or 50 years almost, of quiescence. Giant earthquake used to happen in the 60s. We had 3, 4 of them around the 60s, and then they didn't happen for a long time. I know a few senior seismologists who got very much frustrated about this situation because they entered in their career about this time thinking they would learn something from giant earthquake happening, and nothing happened for 40 years, and then they started to happen again. So we often get this question by journalists: what's happening? Is the Earth angry about something? And of course it's not the case. We think it's just a normal statistical fluctuation. This plot says, and I will come back to that again, you should have one giant earthquake every 10 years, roughly speaking. But of course you can have 1 year with 2 or 3 of them, and then 50 years without any of them. It's just a normal statistical fluctuation. And now, over the last 10 or 15 years, we had already 3 of them, giant ones. And then in Chile, we had, in the year 2014 and 2015, several very large earthquakes. So many things we are learning again from the occurrence of these giant earthquakes, which didn't happen before the year 2004, the year of the Sumatra earthquake. Okay, so that's one per decade, but irregular. That's the take-home message. Now, if you look at all the earthquakes that are recorded by the global network, how do we know that earthquake happened? It's because we have seismological stations all over the world. That's this plot here. Every red dot is a seismological station, and of course there are many more. But these networks allow to detect whenever an earthquake happened inside the Earth. It sends seismic waves. Those waves reach stations. They are recorded, and then we can locate the earthquake. And the sensitivity of the network is such that we can locate earthquake as soon as they reach a magnitude larger than magnitude 4. It used to be 4.5 in the past. Now it's getting smaller as we have more stations. So these are the earthquakes that were located by the global network in the year 2003. That's already more than 10 years ago, 15 years ago, month by month. This month of January, 40 earthquakes were located of magnitude larger than 4.5, so that they were detected by the global seismic network. And then February, it's 29, March is 41, 33, 46, and you get the numbers, 30, 40 per month. So it keeps on going like that, and some months are noisier than others, 47, 63 in September. And then by the end of the year, with 30 to 40 every month, we have a little bit more than one earthquake every day that is recorded by the global seismic network. So by the end of the year, we have 500 earthquakes. So earthquakes, there are plenty of them. So to the question, how many earthquakes do we have? The answer, it depends. These earthquakes that are detected by the global network, we have about one every day of what we call medium-sized earthquake, the ones that are big enough to be located by the global network. Now, if we go to a smaller one, if we put local networks, actually we find that there is a lot of noise. Earthquakes happen all the time. If you go to the magnitude 3, the magnitude 2, they happen every hour, every minute, every second. There are millions of them. And on the other side of the scale, the big ones, the ones that start to kill people, they happen almost every month. The large one, you have one large one every year, and the very large one, the giants ones, like I said, they happen almost every decade. So that's something to keep in mind. The bigger, the less earthquake we have, the smaller, the more we have. And this is a kind of rule of thumb to remember. 1 per hour, 1 per day, 1 per month, 1 per year, 1 per decade. And the real law is the Gutenberg-Richter law, where on a log-log scale, it looks linear. That's the number of earthquakes plotted against their size on a log-log scale, and then the bigger earthquakes, the fewer you have, and the smaller, the more. Of course, there are limitations. We don't know what happens with very, very small earthquakes, if the law is still true. And on the other side is also the same problem. Very large or giant earthquakes are rare, so we don't really know if this law still is valid for extremely large earthquakes. When they happen, we can check. But we have had very few of them, one every decade, so it's slow science. Okay. If we look at seismicity, and that's the core of my talk, 30 years of seismicity, 17,000 events located all over the world. Now we see that earthquakes don't happen everywhere. We have large surfaces without or almost without earthquakes, like the Pacific plate, the South American plate, and of course these surfaces without earthquakes, they are the tectonic plates. And the earthquakes occur around those plates. On the boundary, there are lines of earthquakes, and the earthquakes happened on these lines, which are the boundaries of the plate tectonics, and almost only there. So why do they occur? It's because we have these plates, so that's a sketch of the 12 biggest plates on Earth. It's because, mostly because they move. These plates, they have a motion. And this map here shows the plate motion in a specific reference frame in which the average motion, the total motion, is 0. And it shows how plates move relative to each other with the arrows. The longest the arrow, the longer the velocity, or the bigger the velocity. And the biggest velocity is approximately 10 centimeters per year. So that's something to remember. Plates exist, they move, they have a velocity which is around, at most, 10 centimeters per year. And we can demonstrate that. I'll go back to that a little bit later. One important thing to remember is that plate tectonics is almost 100% horizontal. There are some vertical motions, of course, here and there, especially where there are mountains or subduction zones, but these vertical motions are 1 order of magnitude smaller than the horizontal motions. And I used to teach my students, when we make measurements, whenever you find a vertical motion that is larger than 1 centimeter per year, it's wrong. There's a mistake somewhere. Go check your measurements, your calculation, your process, and everything. It's not entirely true. In some places, we do find vertical motion larger than a centimeter per year, but it's a very good rule, because 95% of the time, it's a mistake. So plate motion is mostly horizontal. Why do we have plate tectonics? It's a little bit complicated, but it can be wrapped up in one slide. It's because we have mantle convection. So this is the inside of the Earth. We have the mantle made of rocks with silicates. There are some radioactivity in these rocks because of uranium and other isotopes. This creates heat. So the rocks in the mantle are very hot. Because they're hot, they're soft. And because they're soft, the mantle behaves in a viscous manner, like honey. So it moves to bring the heat to the surface. Because it moves, that's called convection. And those convection cells, here you have heat going up, and here you have cold going down. So that's the most of the motion going up and down, but at the surface, it's an horizontal motion. This is why you have horizontal plate tectonics of this convection cell. On top of it, you have a horizontal motion that's dragging the biscuit on top of the honey, the rigid plate. So that's why they move. So now we know that there are plates and that they move. Why does this create earthquakes? That's the big question. This sketch is of 2 plates, red plate, green plate, moving with respect to each other in a given direction. So the red plate will be moving to the north, the green plate will be moving to the south. They have a boundary between them, which is here. It's a fault. It's the line that separates the 2 plates. And the problem is this line, this boundary between the 2 plates is rough. It is not something that is lubricated. So when the plates want to move, something will happen here because it's rough. It does not want to move. It stucks the 2 plates together. So what happens is as the plates move north and south, the plates will move and they will never stop moving because they're very big things. But because the limit between them is rough and does not want to move, I'll show again, the plates will deform. Here no motion, here motion, so they will deform. And then when the deformation is big enough, it will break the resistance of the fault. The fault is glued, but with the glue has some level of resistance. When this level is reached, it breaks. Now, this explains why you have earthquake, because the plate will deform in an elastic way, accumulate deformation until it's too much. And then what has been accumulated in several years, decades, centuries will be released in one instant, seconds, minutes, and that's the earthquake. Now, if you have the same thing, the same 2 plates moving at the same velocity, but a stronger fault that does not want to break when you have accumulated this much of deformation, then it will simply keep going. and accumulate more deformation until you reach the level of resistance of this fault, and then it will break. But it will break harder because more deformation was accumulated. So in the end, the earthquake in the first case was this size, and the earthquake in the second case is double the size because it accumulated deformation for double time. Very simple calculation. You accumulate more deformation, you break less often, but when you break with a bigger earthquake. So that explains why you have earthquakes and also why you have small ones and big ones. It, in the first instance, depends on the resistance of the fault. Of course, it also depends on the velocity of the plate. If the plate moves with a larger velocity, you accumulate faster the same level of deformation, and you can generate more often the same earthquake, or less often an even bigger one. So that also explains why on my plot you have more earthquakes and more large earthquakes around plates which move fast. The Pacific plate, for example. Now, of course, the beauty of it and the beauty of nature somehow, some people don't find this beautiful, but is that it speaks, the language of nature is mathematics. The deformation of the two plates, my red plate and my green plate, this is just a drawing, it's just a sketch, except that the deformation curve here is not just any curve, it's a mathematical curve. And we can demonstrate using elastic medium law of deformation, and it's something that has been done a long time ago. The screw dislocation model was invented, or probably not invented, but explained and applied to plates as soon as 1964, my birth date. And so it simply says that this curve is not any curve. To the first instance, it looks like a very simple mathematical formula. It's an arctangent, which means we can calculate how much the plate should deform, and then we can check in nature that this is actually the case, that the plate does deform with this formula. And if that's not the case, then it's a deviation from theory, and we have to understand why and what's going on and everything. So this is what we've been doing, measuring deformation, motion of plates and deformation of plates to check that this formula is actually real. How we do that is with geodesy, and nowadays with space geodesy. And in my case, and in the case of many of us, it's simply GPS. We can also use now the other satellite positioning system, like the Russian one, GLONASS, the European one, Galileo, and there will be a Chinese one, Baidu, and there will be an Indian one. So it's a general scheme that we have now the capacity of measuring our position anywhere, everywhere on Earth using satellites. It's difficult to explain how that works in a couple of minutes, so I just give you one slide to explain how the GPS system works, and more or less everything, all the systems work the same way. The thing is, we need to be able to measure a position accurately at the surface on Earth everywhere. Everywhere, anytime. That means we need not one satellite, that we would have to wait the satellite to come back over our head once in a while, but we need a constellation of satellites. So GPS constellation, you have 30 satellites orbiting around the Earth. That means you will always have several of them above your head. And how we use the GPS to measure our position is because the GPS satellite is sending all sorts of signals to the station. And to wrap it up in a nutshell, these signals have codes, and these codes allow to measure the travel time of the GPS signal from the satellite to the station. It's like the GPS satellite has a clock. It says, this is the time I'm sending you a signal. The signal travels, it arrives at the station. The station also has a clock and times the arrival of the signal. The difference of time is the travel time, provided you have the good time at both clocks, and that's a problem, but we know how to solve this problem. So we measure the travel time, knowing the speed of an electromagnetic wave, which is approximately the speed of light in an empty space. We can calculate the distance between the satellite and the station. That's the game. Once you know the distance, everything else is easy because we know where the satellites are, because that's their orbits. They're far away from the Earth, 20,000 kilometers. So they have very regular orbits. We can calculate and predict a long time in advance. So we know where the satellites are. We measure the distance. And then it's just a matter of triangulation between at least 3 satellites to determine our position. That's how GPS works. The magic of it is we all have GPSs in our phones, in our cars, and they have a precision of about 2, 3, 4, 5 meters. The one we use, thanks to dual frequency, thanks to processing of the carrier phase, thanks to all sorts of magic we do to the data, we reach a precision of about 1 to 3 millimeters. That's the thing. So it's not easy to do, but that's the thing to understand. Public GPS is 5 meters. The scientific GPS is a couple of millimeters of precision. So what we do is we do this all over the world. We install what we call geodetic markers. So this is one mark inside a rock, that's bedrock. So it's supposedly representative of the plate. You have a tectonic plate, it has rocks. Some of them comes to the surface. In these rocks, we put markers. Markers could be anything. A simple nail, a screw, a cross engraved on the rock, anything that will locate the position. This is the mark. And then we bring a GPS, that's a GPS antenna, it's about this size, that we put on top of the marker, and we acquire data for several days of GPS data. With these data, we can measure or calculate the position of the antenna, and knowing that the antenna has been installed exactly on top of the marker, we know the position of the marker. We will do this several days in a row, wait a couple of years, come back, and what we see is that when we know the position, so that's, okay, you come year 1, you know you're here with a given uncertainty of several millimeters, and then you will wait and you repeat the measurement a second year, a third year, fourth year, and so on, and you'll detect that the point is moving. It's moving because of plate tectonics and some other things. And this motion, of course, it's just here in this case, it's a linear trend, it's a constant motion. We have 1 centimeter added every year, so in the end we have a velocity of roughly 1 centimeter per year. This is how we measure plate tectonics, and this is how we demonstrate that plate tectonics is real. We can also, instead of coming back every year, we can leave the instrument and accumulate data every day. And those we call permanent stations. There are plenty of them. And with those, we can have not 1 point every year, but 1 point every day, for example. And in that case, so this is how it looks, 1 point every day, so that's a small zoom inside this. And this station has 10 years of measurements between 2004 2014, and we see the station moving day by day with a little bit of noise. That may be the uncertainty of the measurement, that may be something else that adds to the linear motion of the plate. Of course, the average motion can be determined with a high precision after 10 years of displacement. If each position has a precision of several millimeters, we know the velocity with a precision of less than a millimeter, in that case 24.3 millimeters per year plus minus, something small. And once in a while we see those things happening, a break in the time series. That's an earthquake, of course. A small one, maybe, or a big one that is far away from the station. So this is how we study plate tectonics and deviation from linear trends that are caused by all sorts of phenomena, including earthquakes. One of the major findings or results coming from GPS is that using all GPS stations all over the world, this is what we get, the International Terrestrial Reference Frame, ITRF, determined by GPS. So it's a number of stations globally distributed, for each of which we have a position at a given date. So that's ITRF 2008. It's reference to some date. At this date, the position of the station is so-and-so, and the velocity of the station. The velocity are the white arrows plotted here. And the discovery here is that the motion we measure today, the few centimeters per year we measure every year nowadays, is almost exactly equal to the thousands of kilometers accumulated over hundreds of millions of years. You've had talks about geological plate motion, how plates move 200 kilometers within 10 million years. And that's the discovery. The small centimeters of motion every year adds up to the hundreds of kilometers over millions of years. In most places, not everywhere, and that's why science is interesting. You always confirm something, but, and then the but is interesting. The but says, for example, if you look at small plates, like Arabia, India, South America, that's already an old drawing, so we have few GPS measurements, but nowadays we have a lot more. The geological velocity of the plates, the hundreds of kilometers divided by millions of years, but in terms of velocity are in yellow, and the GPS measurements are in red. And at the first order they match, they are of the same amplitude, so that's good, that's fine. We are not saying that plate tectonics is totally different from what geologists say, but still there is a small deviation, and in some occasions not so small. For example, Arabia, the geological model says 3 centimeters per year, but GPS finds only 2. And it's true all over here, it's also true here. India, same. The geology says 5 centimeters per year, but GPS is only measuring 4. South America, the convergence between Nazca and South America, geology says 8, GPS says 7. So that's, these numbers are really interesting, and they've been subject to many discussions between geologists and geodesists. I am a geodesist, saying, well, some of us said geology is wrong, some of the other guys said GPS or geodesy is wrong, and obviously it's not that. It's much more interesting, everybody's right, but plates do change velocities. They could have had one velocity for the last 10 million years, but nowadays it is slightly different. And in this meaning, it's interesting to see that it's small plates that have velocities that are nowadays slightly different from velocities they used to have in the past. And in that case, it's the 3 plates slowed down because of things we can understand. For example, India has been pushing the Tibetan plateau into Eurasia, and this is very difficult to do. So as India has been moving northward over the geological timescale, it's been slowing down. 60 million years ago, it was moving 15 centimeters per year, and now it's only, I'm telling you, the geologist said 5, I'm telling you 4, because the slowing down continues. That's also something we can study. We confirm plate tectonics by directly measuring it, but then the deviations can also be analyzed in terms of dynamic of plate tectonics, changing plate tectonics over time. I need to rush a little bit. So that's something else we've been doing with GPS measurements. For example, identifying new plates or smaller ones that we didn't know about before we went there, measured the position, measured again, and detected a motion that was not expected. For example, this part of Eurasia, which has all the vectors in red, was supposed to be attached to the Eurasian plate, sorry. So this was supposed to be Eurasian plate. And in a reference frame where Eurasia is not moving, by measuring about 60 points in all these places, we detected that all the points in Southeast Asia were moving with a motion towards the east, of about 1 centimeter per year with respect to stable Eurasia. And so this platelet was called Sundaland platelet, and the motion of this platelet was established by GPS. There are plenty of other things we can see here. For example, we had two, that India was slower than suspected or anticipated. And then because we also had several points in Myanmar here, we could measure the velocity of this large fault here, which geologists and tectonicians, the name of the fault is Sagaing Fault in Myanmar. Geologists and tectonicians thought the fault was moving with a velocity of 5 to 6 centimeters per year. We found only 2. So, of course, because you've seen my small cartoon at the beginning, if the fault is moving at 5 or 2 centimeters per year, makes a huge difference with respect to seismic hazard. So that's one of the consequences of all these measurements, is to re-estimate, reassess seismic hazard on all faults, because we have more precise knowledge of their velocity than before. And sometimes it makes a big change. Okay, on to South America. That's all the measurements that have been carried on by, for example, my German colleagues in GFZ Potsdam, in Chile and Argentina over many years, showing what? Showing that the plate is not only moving, but actually deforming. You can see here that all along the coasts, you have longer vectors than inland. Inland in Argentina is almost 0. So that's fixed, not moving. The plate is moving, that's moving with the plate, but this point is moving inland with respect to what we call the stable plate interior. And this motion is decreasing as you go to the interior, and this decrease of the motion can be predicted by the elastic curve, the screw dislocation model, the arctangent model, slightly modified. But the important thing is, on this map here, so these lines show the model, and the triangles show the measurement. So the agreement is pretty good. So the first conclusion is that the deformation of the plate is indeed accounted by the mathematical formulation of the screw dislocation. Works well. And it shows that the plate is compressing because of convergence of two plates, because of roughness of the fault, and so accumulation of deformation that will be released in earthquakes later. But there are deviations. If you look in these sections, you have many measurements that actually, and here it's pretty obvious, that don't fall on the line of the curve of the prediction. The measurements actually say here there is no deformation. All the points have the same velocity. The trend is 0 deformation here. Here is the same, 0 deformation, when the model predicts a lot of deformation. So this is now well known, but at the time it was not. And we kept making more and more and more measurements in Chile, in South America, to investigate this. And this is a map with there are about 300 points with measurements all over Chile from 40 to 20 degrees of latitude, so that's about 2,200 kilometers. And what we discovered is that there are places with a lot of deformation. Those places are plotted in black, and places where deformation is not so big, even comes to 0, and that's the red going to orange, going to yellow. So what comes from these measurements is that instead of seeing the faults, the subduction zone, showing compression from south to north all the way of this plate, we see that compression is very heterogeneous. There are places where you do have compression, here, and places where you don't have, or even less. You have almost no compression. So it's like a patchwork of places accumulating deformation, places not accumulating deformation. And that's due to the roughness of the fault that is not constant. In some places, the fault is very rough. In some places, it's slick, and it does slip without resisting the slip. So in some places, you have deformation because it's rough. Some other places, you don't. I need to rush that. And so what we plotted here is the amount of coupling, what we call the coupling coefficient. If it's very rough, it's very coupled. If it's coupled, so the coupling goes from 0 here to 1 here. And so you see that you have lengths of high coupling and then narrow areas of low coupling. And of course, those areas really match earthquakes. So these are the last 3 very large earthquakes in Chile, 2010, 2014, 2015. And this is the size of the rupture, the size of the rupture here, the size of the rupture, and they always occur on top of black areas of coupling where the accumulation of deformation was very strong. So easy to predict where are going to occur the next earthquakes. So I crossed the word prediction. Please remember, we never predict earthquake. We never do that. We never know for sure. But we can assess the level of risk of an earthquake happening here. The thing is, we now know where, thanks to GPS, but we still don't know when. That's the problem, because we don't know the roughness of the fault. We don't know exactly how much, and so we don't know if it's going to break tomorrow, next year, or the next 10 years. So we don't make predictions. We make evaluations of areas that are at risk. And if we do that, that's what we see. We have all those patches that are black with high coupling, but without recent earthquakes. By looking at the history of earthquakes, we can discuss a little bit what's going to happen. And our estimation is that, for example, this is coupled, but it won't break soon because it's in between 2 ruptures that already occurred and which decreased the strain here. This here is also coupled, but it will not break soon because it needs more accumulation of deformation, like in my small sketch in the beginning. Many reasons for that. And the area where we think a large earthquake is going to happen next is this one. And so we put more instruments in this area to be prepared to capture the next earthquake. So because I'm out of time, I will skip this part just to show you, okay, this one. That's what happened when we have GPS measurements acquiring data every second, not every day, not every year, but every second at the time of an earthquake, when the earthquake occurs. So the stations are working. And so the earthquake starts here, the rupture propagates, and when the seismic waves hit the GPS stations, they start to move. And the arrow shows the motion of the GPS station. This station on the coast here moves by 5 meters. 5 meters is 3 centimeters per year, accumulated for 170 years. That's the time of the earthquake before. And then, 170 years later, it breaks and it released the 5 meters in. That's the time here. So you have about 80 seconds. After 80 seconds, you have 5 meters of deformation. And by analyzing those records, you'll notice, for example, look at this station. It starts to move to the south, then rotates, almost stops, and then elongates again. And this curve is the last slide I will show. So this is this station, moving with this motion, first to south, then stops, and then elongates to west again. This is a very strange motion. We have a lot of difficulties to reproduce with mathematics and models. And we have still a lot of things to learn from these events occurring. It's like the earthquake could have stopped here, and that would be the end of it. But then it started again and became a bigger earthquake. So that was one of my points. How earthquakes become very big, we don't know. But it's by analyzing those records that we have the hope to be able to tell in the future. Thank you. Sorry for being too long.